All right. I think hopefully maybe we can get the last of this done in maybe one video. I don't know. This is going to probably be too long of a video. I don't know. We'll see. Maybe these questions go faster. Who knows? Okay, so we're number 18. It says estimate parameter values and interpret. A random sample of college students were asked to record how many hours they sleep per night during final exams. Not many. In 22 students, the mean was 5.77 hours. Seems about right. With a standard deviation of 1.72 hours. Construct a 95% confidence interval for the mean number of hours slept by college students during final exams. On average, are college students getting significantly less than 8 hours of sleep each night during final exams? Okay, part A says to give a point estimate. So the real question is, are we talking about proportions or means? That's the one thing we really need to know in order to decide if we have a point estimate decide what symbol we're going to use for our point estimate, right? We have to know. Well, as I'm reading the question, it looks like I'm seeing some stuff about, means in here, right? I see this guy, the mean was 5.77 hours in the 22 students, right? Well, here's some good news. That's your point estimate. X bar. Remember, X bar is for a sample mean. And X bar is the symbol we use for point estimates for means. And it's given to us in the problem. So we actually don't have to calculate anything. So isn't that handy, right? Okay, so we've got our sample mean here. And then as our point estimate. So part B says to find a confidence interval. So let me, let's see here. Sorry, I'm looking at my formula sheet so that I can see what it says to do to find a confidence interval. I need to write down some stuff though. Let's come through and write down all of our important information. So random sample, so that's important. So it's random, that's good. I know we have some criteria, right? We just gotta make sure our sample size is bigger than 30 or it's normally distributed, which actually doesn't really say that in here. I think we're supposed to just assume these things. So I'll tell you this. On your final, I will not be asking you to verify any requirements. They will all be assumed, I think. Yeah, you can basically assume that they're satisfied. I think most of them will tell you that they are satisfied and you don't have to worry about it. So you're fairly safe to just calculate freely without having to worry about satisfying requirements and such. But I'm looking at this and I'm questioning if my conditions are satisfied because it doesn't say that it's a normal distribution or anything like that. And my sample size is fairly small. Anyways, all right, let's move on. So in 22 students, okay, so what is that? N is 22. All right, the mean, 5.77, so X bar equals 5.77. The standard deviation, S, 1.72 hours. Well, didn't change color. There we go. Confidence level is 95% or 0.95. Okay. And then it'll ask us about, are they getting less than 8 hours, significantly less than 8 hours? So we're going to keep an eye on that guy over there. That's going to be important somewhere. We'll figure it out. But for the confidence interval, I don't think that part's important. So let's go with this. So if we're doing confidence interval on means, if you look on your formula sheet, you'll find where it says parameter under chapters 9 and 10, means, and for confidence interval, it says we're doing a t interval. So t interval. Okay. And we will go on the calculator. And this is going to be under math. No, what am I doing? When did I ever go to math before? Stat, tests, and then T interval looks like it's number 8. Okay, notice at the top it says T interval. I just pushed the number 8 instead of scrolling down. Okay, I have stats this time. I don't have data. So go to stats. My X bar is 5.77. My standard deviation is 1.72. My N, 22. Confidence level, 0.95. I think it's already there. And calculate. Okay, here we go. So I think we're going to round to, I don't know, let's go with 3 decimal places because our data is out to 2 decimal places, so we'll do one more than the data. Of course, I think I'm looking on my key and I did them out to 2 decimal places, so I'll go ahead and just do it out to 2 then, I guess. Okay, so this is going to be 5.01, 6.53. So let's see here. 5.01. I think we really should do 3 decimal places. I'm sorry, I'm going to do 3 decimal places. That was 007, and then this one 6.533. There we go. Okay. Okay, so this is our confidence interval. So this is what we're saying, that we're 95% confident that the mean number of hours that... Okay, hold on. Part C says interpretation. So we will say we are 95% confident that the mean number of hours of sleep that college students get during final exams is between 5.007 hours and 6.533 hours. Okay. Hours of sleep. Oh, I'm sorry. I've missed something that's kind of important that I'm going to put here. Per night that college students get. Yeah, I should have said that. Because that is kind of a big difference. Mean number of hours of sleep that they get during final exams. I should say per night, because that is an important distinction. So per night. Okay, and so what's our final conclusion? The question says, this is where we need that less than 8, right? On average, are college students getting significantly less than 8 hours of sleep each night during final exams? So I would say, yeah. I mean, look at this. On average, they're getting between 5 and 6.5 hours of sleep per night, right? I think that's a significantly low number, like a lot less than 8, right? I would say that's just significant. So yes, on average, college students are getting significantly less than 8 hours of sleep each night during final exams. Okay, here's our next question. If a confidence interval for a mean is 23.7 to 25.2. Find both the point estimate and the margin of error. Make sure to use proper symbols. Okay, so I just mentioned how the point estimate for a mean is going to be X bar. That's my symbol, right? So here's my symbol. This is my, actually, let me do this. I'm going to go ahead and write point estimate. X bar. And then for margin of error, capital E. Okay, so if we're given an interval, then we need to take the point estimate is the midpoint of your interval. It's like right in the middle, right? So if I were to draw a number line, it's the point that's halfway between 23.7 and 25.2. In other words, it's the average of those two numbers. So if I take 23.7 plus 25.2, and then I divide that in half, okay, then that's going to give me my point estimate. That's the point right in the middle. So this number should be somewhere between those two numbers, and it should be exactly halfway. Well, if I divide them, add and then divide would be 24.45. So that's my point estimate. Okay, and then the next question is find the margin of error. Well, how do I find the margin of error? Okay, so I'm going to draw a little picture here. Here's your 23.7. This is your 25.2. And right here, this is 24.45, right? Halfway between. So, so I want to know what is my margin of error. So I want to know the distance from here to here, or the distance from here to here. These are the same. Both of these are E. That's my margin of error. All right, so how do we find that? Well, the distance, right, or from here to here, subtract. So either 25.2 minus 24.45 or 24.45 minus 23.7. Either way, this is going to be, let me just mark this here. I'll do 25.2 minus 24.45, and I get 0.75. There you go. Easy as that. Okay. C. In a random survey of 3,611 adult Americans, it was found that 542 had made purchases on their smartphone. What is the point estimate for the population proportion? Sorry, I want to come back here really quick and just highlight that this says it's for a mean. Okay. Point estimate, population proportion. Okay. There we go. So what's the point estimate for the population proportion of adult Americans who make purchases on their smartphones? Report this estimate with the proper symbols. Okay, so now if we're talking about a point estimate for a population proportion, we are looking at this symbol, p hat. Okay, and in order to find p hat, if we have an interval, which we don't, but if we had an interval, we'd find it exactly the same way as we just did in part B, right? We would find the midpoint of the interval and then all that kind of stuff. Now, if we don't have that and we're asked to find a point estimate, so like on the previous part, on part A, it asked us to find the point estimate. And for means, it's just the sample mean. And for proportions, it's going to be this formula, x divided by n. Okay, which is actually not too challenging if you think about it. I mean, this is how we find a proportion anyways. It's like the part out of the whole, right? It's a sample, well, not sample proportion. It's, wait, is that the symbol for, I don't think so. So anyways, so this is how we're going to find it. X divided by n. And let's see here. So what's our x and what's our n? So let me color code. Usually I do red, I do N in red, so I'm going to do that. In a random survey of 3,611 adult Americans. Okay, and remember the X is going to be the number, of course I didn't write it down. X is going to be the number of people with some certain characteristic that's being asked about, right? So the certain characteristic would be people that made purchases on their smartphones. Okay, so there's 542 of those. Okay, so now we have that, all we have to do is plug it in and calculate. So our 542 out of 3611. So p hat is equal to, drum roll please. No, I'm just kidding. 0.1501. There we go. Little hat got kind of hidden there. There we go. All right, so that's all of page 11. That didn't take too long. Well, 15 minutes, I guess. Okay, so page 12. Oh, part B says, construct a 90% confidence interval for the population proportion of adult Americans who make purchases on their smartphones and interpret this interval. All right, so let's write down everything that we just had on the previous page. So let's see, we had x equals 542. We had n equals 3,611, right? I think that's all we needed from the previous page. So let me highlight some keywords here. We're looking for a 90% confidence interval. Population proportion. Those are important things, right? And interpret. Can't forget that part. You won't, though, if it's multiple choice. It'll tell you. Okay, and then last thing is our confidence level, right? We need to know our confidence level. Confidence level is 90%, or in other words, 0.90. Okay, so let's see here. We're doing a confidence interval for a population proportion. On our formula sheet, let's see. Weeks 9 and 10. Proportions, confidence interval says 1 prop z int. 1 prop z int. Okay. So let's see here. Proportions. Let's go on our calculator. Stat. Tests. 1 prop z int. Oh, there it is. A. All right, my x was 542. My n, 3,611. Confidence level is 0.90. Calculate. All right, here's your confidence interval. 0.140 up to 0.15987. Let's see. Well, if we round that, 0.1598 is going to round to 0.160. Okay. So let me do that. Oh, and you'll notice that your p hat was there. See that? 0.1500. We could have probably just said 0.15 for the p hat. But there it is. Okay. So here's my confidence interval. 0.140, 0.160. Okay. And how do we interpret this, right? Because this is the second part of the question, is to interpret. So we would say we are 90% confident that the proportion of adult Americans who make purchases on their smartphones is between 0.140 and 0.160. Okay. Number 19. Test hypotheses and understand concepts behind hypothesis testing. Distinguish between statistical and practical significance. All right. Letter A. A statistics student heard that an individual's arm span is equal to the individual's height. To test this hypothesis, the student used a random sample of 10 students and obtained the following data. All right. Sorry, I got all my paper spread everywhere here. Let's see what it says. Student number. So at the top, this is just identifying each of the students. They could have put a name or anything, but this just assigned a number to every student in this study, and gave the height in inches and the arm span in inches. Okay, so arm span, just in case you're wondering, is if you hold, like they say, wingspan of a bird, right? It's like from the tips of the wings, if they hold the wings all the way out. So for arm span, if you hold your arms all the way out to the side, it's from like your middle finger to your other middle finger. Presumably that's your longest finger on your hands. It is on mine, just barely, but it is. So anyways, you hold your arms straight out to the side and they measure that, and then they say that that's supposed to be the same as your height, right? I don't know if you guys ever heard that. I thought, like, I grew up and we heard that. People talked about it all the time. Apparently that's not like common, I guess, conversation. So I don't know, that's just what we always talked about. So we would, as little kids, we'd take our arms and we'd like stand up next to the wall and put like one hand down by the bottom of the floor and then the other one up as high as we could. And then we'd hold our finger there and then we'd stand up and see if our head came to that same height. So we actually would test this, right? We tested this hypothesis as children. Okay. Anyways, we're going to do it, as statisticians now. Okay. Now we're adults, so we got to do this the adult way. All right. Test had a 5% significance level if height and arm span are significantly different. Okay. So if they're not significantly different, then that means that they're pretty much the same, right? Pretty close. Okay. So what type of hypothesis test is being run here? So we need to figure out what is, what do we have going here? Are we talking about mean? Are we talking about a single mean? Are we talking about two means? Are we talking about proportion, a single proportion or two proportions? Things like that. Because remember, chapter 11 talks about all of, the two means and the two proportions and stuff. This one here is an example of having the two means, okay, because we have height in inches and arm span in inches. So, and these ones are matched up, right? This is a matched pairs test. These are, so when it says what type of hypothesis test is being run, we're going to say this is a two means dependent matched pairs. That's what this is. Two means. They're dependent, right? Because it depends on the student. When you pick the student's height, then you automatically picked their arm span because it's that same student, right? So two means dependent matched pairs. Okay. So then the next question says, what is the hypothesis test? Or it says hypotheses, right? So if you look on your formula sheet, you'll see under chapter 11 where it says two means dependent matched pairs at the very bottom. You'll see that your null hypothesis is stated this way. H naught is mu d equal to 0. Okay, so that's going to be your null hypothesis for a dependent matched pairs problem. Mu d equals 0. What this means is that the difference of the means, or the mean of the differences, I think it's the mean of the differences, we're saying is 0, right? So if you take all the differences between the height and the arm span, so difference means you subtract them, right? Which we will do here in a second. So you would subtract them, then you would take the average of those differences and find out if it's going to be, if it's about 0, then that means that they're pretty much the same, right? There's not a lot of difference. But if they are fairly different, not 0, right? Then they would be they're different, right? So when it asks us, we need to figure out our hypothesis test, right? So we're looking for specific kind of words, right? Either less than, greater than, change, different, increase, decreased, anything like that, right? Test at a 5% significance level if height and arm span are significantly different. Different's that word that we were looking for. So if we see the word different, then we would say not equal to 0. All right. And that would be our hypothesis test. I'm sorry, that would be our hypotheses. Now we need to find our test statistics. So in order to do that, we are going to have to put this stuff in our table, or I'm sorry, our lists. So list 1, I'm going to call height is list 1, and arm span is going to be list 2. And list 3, okay, list 3 is going to be the difference between list 1 and list 2. Okay, that's how we're going to find that. So, and it honestly doesn't really matter how you do this, because no matter what, when you add them all up and you find your difference, it'll, we'll see what it looks like. So we have to find list 3. So what I'm going to do is I'm going to pause it. I'm going to put my lists in, and then I will go ahead and I'll show you how to do list 3. I will do list 1 and list 2 first. Then I'll show you how to do list 3. Okay, so I've got the calculator here. I've got my first 2 lists put in, list 1 and list 2. Just again, I want to remind you that when it is a matched pairs test like this, you do have to keep them matched up. I think that pretty much goes without saying, but you never know. So yeah, we're going to be doing a t-test on list 3, but we have to know, because we have to know the difference, right? So so here, if you highlight L3 where I have it in black, you're going to type in your equation. What we want to do is do L1 minus L2. So I'm going to, down here in blue, you'll see right above the 1, it says second 1, and then minus second 2. Hit enter, and there you go. So these are all your differences. Okay, some positive, some negative. That's okay. It's supposed to be like that. So we've got some positives and some negatives. Okay, so now let's go back to our stat tests, and we're going to do the t-test on list 3. So t-test, we have data, so we're going to go over here to data and hit enter. And we're going to put in mu naught. This is where we're going to put 0. Okay, because remember, that's the thing, and I should probably write that down on the notes there, that this is our mu naught is 0, because that's what our mu sub d is equal to, right? And then our list 3 is what we want to keep here. Keep frequency as 1, and we're testing if it's not equal to. So hit the not equal to, and then do calculate. Side note, if people are having issues with drawing, if you wanted to draw the graph and look at it, you might have something stored in one of your other graphs. If you're getting an error and it won't draw it for you, you might need to go and like clear out anything in your y equals or your stat plots, make sure they're turned off. That could be causing you any issues. Okay, hit calculate. Okay, here we go. So we've got our test statistic here at the top, and that's the negative 0.39. Okay, and then we've got our p-value right below it, 0.7039. And we also have x bar here, standard deviation, sample size 10. We don't need these other things on the bottom there. We just need the first two, the t and the p. Okay, so let's go back. So our test statistic is what we're going to call our t-value. So test statistic, t naught, is equal to negative 0.39. And I guess I just called it t. We'll just call it t. Okay, and our p-value, so the next question, so let me write here, t-test on L3. And up here, let me make a statement that mu naught is 0. That's that guy. Okay. All right. So just side note, when you're doing a dependent matched pairs hypothesis test, your mu naught will always be 0. Always, for the dependent matched pairs. Okay. So for p-value, p equals 0.7039. Okay. And then it asks for a final conclusion, right? But what we didn't do yet is determine, so our alpha here, what is our alpha? 5% level of significance, right? So we need to make a conclusion. So over here, I'm going to go ahead and state alpha equals 0. I'm going to show you two ways you can do this, 0.05. I guess I'll start, okay, sorry. Let me start up here with the test statistic if you want to go that route. Okay, so we've got our test statistic, right? We would need to find the t critical value. Okay, so the critical value is if we are doing, so we're doing a two-tailed test, right? This means we're going to need a plus and minus t alpha over 2. Okay, so we need to know the degrees of freedom and we need to know our alpha. So I'm going to write up here 5% level, significance level. So alpha equals 0.05. And then underneath that, I'm going to go ahead and say alpha divided by 2 is 0.025. And then I have my degrees of freedom is something else I'm going to need, degrees of freedom. Degrees of freedom are found by taking n minus 1. So n is equal to 10. So we get 10 minus 1, which is 9. Okay, so I'm looking up degrees of freedom is 9. Alpha over 2 is 0.025. See, this is like actually quite a long route to take, by the way. P-value is much better. It's much faster. But I want to demonstrate. I think I'm going to actually pause so I can pull up the formula sheet on here so I can show you the t table. I know people were having some trouble reading the t tables. So let me pause. Okay, so in hindsight, I probably should have been pulling up the formula sheet, you know, every time we've been doing notes. And I mentioned the formula sheet, but I mean, it just is a lot of work to keep pulling it back up and changing screens and stuff. So anyways, but for this one, I know it's important. So I'm going to go ahead and show this. Okay, so we've got our degrees of freedom, 9, our alpha over 2. Now, I just want to be clear. The only reason we're doing alpha over 2 is because this is a two-tailed test, right? It's not equal to 0. So you've got the plus or minus t alpha over 2. That's why it's t alpha over 2. Otherwise, it would just either be a negative t alpha or a positive t alpha, depending on whether or not you're like if you're doing less than or greater than, right? So I just wanted to be clear on why I'm doing alpha over 2 and why it's a plus or a minus. Okay, so let's go to our formula sheet here, and I'm going to show you on the third page. I don't know why there's a white box in the middle. Okay, here we go. Okay, so what we're looking for on the left side here is your degrees of freedom, and across the top is the area in the right tail. So we've got into two. Here's the thing. It depends on if this is the right tail, then you just make this a positive number. If it's the left tail, you just make it a negative. That's the only difference, right? Okay, so if I'm looking at 0.025, that's here at the top, and I don't think I can write on this page. I can't write on this page, so I can't show you by circling. And then I'm going to come down to where 9 is my degrees of freedom. So if I come over here, that's 2.262. Okay, so let's go back. Plus or minus 2.6. Wait, what was it? 2.262. There it is. Okay. Oops. 2.262. Okay, so now let me show you how we can actually use that. So I'm going to draw a little picture over here. Okay. So our critical values, we've got negative 2. Gosh, I can't handle that. 262. And then over here, I've got positive 2.262. Okay, and then my critical regions, these are critical regions here. Okay. So if your test statistic is outside in the critical regions, then you would reject your null hypothesis, right? If it's within, you do not reject, right? So our test statistic here is negative 0.39. Okay, well, let me just start off by putting, this is 0 right in the middle, right? Okay, so negative 0.39, that's about there. Yeah, it's pretty far in the middle of our So if it's inside there, this means that, so if it's in here, do not reject the null. Okay. So from the test statistic, we would say we do not reject the null hypothesis. Okay. Now from the p-value approach, our alpha was 0.05, right? So alpha equals 0.05. So let's compare. 0.7039 is by far greater than 0.05. So if p is greater than alpha, do not reject the null. Okay, so now I know everybody's thinking, God, why did she spend so much time doing the whole test statistic critical value, the classical approach, if it took us 2 seconds to do p-value approach? Exactly. That's what I'm saying too. Let's just do the p-value approach. I mean, why do the classical approach if you don't have to? Now listen, I get it. Sometimes the graph just makes more sense and you're looking at a picture and a visual. That's fine. I just feel like there's a lot of room to make errors there. So, what I would recommend is to just do the p-value approach. So I think on the majority of our questions here, I will only do p-value just because we don't want these videos to take forever. And I think pretty much everyone's going to do p-value approach anyways. But I did want to give at least one example to demonstrate how you would do the classical approach just in case. Okay, so our final conclusion. We're deciding that we're not going to reject the null hypothesis. So what that means is that there is not sufficient evidence at the alpha equals 0.05 level of significance to conclude that how did they say it up here? Height and arm span are significantly different. Okay, so that's that question. All right, next page. 13. All right, it is believed that 85% of Americans eat salad at least once per week. I tend to disagree with that. I don't know who believes that, but all right. Believed 85% of Americans eat salad at least once per week. Okay, a nutritionist suspects that the percentage is higher than this. Is that crazy? She thinks it's higher. I don't know. I just assumed. Oh, it does say she. I just assumed the nutritionist was a female. I don't know why, but it does say she. I think that's crazy. I think she's crazy. There's no way it's higher than that. Okay. She conducts a random survey of 200 Americans and finds that 171 of them eat salad at least once per week. I feel like this is a biased study. I'm just saying. Maybe she's only interviewing like people like at a gym or something that work out and eat salads. I don't know. Anyways, yeah, I'd like to know how she got her random survey. I wonder if there was so many biases in there. Anyways, use a 0.01 level of significance to test her suspicion. Okay, so hypotheses. What are our hypotheses? So first we need to figure out what is our parameter. I mean, are we dealing with proportions? Are we dealing with means? What are we dealing with here? Well, I would go with proportions because, well, I see a proportion. There is a percentage, right? So it says it is believed that 85%, this is what I want, 85% of Americans eat salad at least once per week. Okay, so this is our P. Actually, that's P naught, right? Because when you do your hypothesis test, you've got your P as your parameter. So this is a proportion. We're going to use parameters. Okay. Proportions. All right. So when we do H naught, H1. Okay, H naught, we're going to use P and P. Remember that when we do our hypothesis test, that you're only using parameters here. You're only going to be either using P or mu for in our class, right? I mean, it could be something like P1, mu1, mu d, but that's it. It's not going to be, there's not going to be anything else. It's never going to be an X bar. It's never going to be a P hat. Nothing like that, right? It's only ever going to be either a P or a mu. P for proportions, mu for parameters, okay? Which it clearly states on your formula sheet, right? So first, null hypothesis always P equals, okay? So P equals, and then that is always going to be given to you in the problem. No matter what, if there's only one percentage in there, that's what's going to be here. This is your P naught is 0.85. So we will always put this here and here. Okay, and then the next question is, what am I going to put on my alternative hypothesis? Is this going to be less than, greater than, or is it going to be not equal to? And so you have to read the question and look for those key words, right? So where's my key word? I see a nutritionist suspects that this percentage is higher. Higher. Okay, so higher means greater than. Okay, so there's our hypothesis. Our test statistic. Okay, we're doing only one proportion, right? This is a one proportion here. So when we are doing our hypothesis test, it's going to be a one prop Z test, right? Because one means, well, one prop, I should say. One prop means you have one proportion, and a z-test is going to be used for proportions. Remember that for proportions, we use all the z stuff. So let me put a little note up here. Proportions, z stuff. And for means, t stuff. Okay? So when we're talking about, every time you see, like that we're dealing with proportions, you'll notice, like, I'm going to actually point this out. Ooh, I have the formula sheet. Let me point it out. Okay, look here. Notice where it says P for proportions. Okay, and then look over here. You got one prop Z int. One prop Z test. Okay, let's come down here. Two proportions. Okay, two prop Z test. Two prop Z int. Okay, notice that all of them say prop, first of all, for proportions. And then you've got the Z part. And you'll notice that for an interval, it says int. For a hypothesis test, it says test, right? I think that's pretty helpful. And then for the means, you'll notice here, it says T interval, T test, okay? For all the two means down here, you've got two sample T test, two sample T interval. T test on L3, T interval on L3. Okay, all of them, once again, you're seeing those key things that I said. The T's go with means, test goes with a hypothesis test, interval goes with an interval, or int, right? So I think that's an easy way to kind of remember. I know some people had expressed being a little bogged down with all of that calculator stuff and knowing whether it's one prop Z int or, you know, T test or whatever. Hopefully that'll help you, just at least knowing if you know, okay, int is for intervals, test is for hypothesis tests, right? And then if you know that the Z things go with your proportions, the T things go with your means, there you go. All right, let's go back. Okay, so we are doing one prop Z test. Okay, that's what we're looking at here. All right, so for our test statistic, so let me go into our calculator, demonstrate this. This is what takes the longest. Okay, so stat, tests, we're looking for one prop Z test. There it is, number 5. Okay, and our P naught, which again, like I said, is always going to be given to you in your problem, and that is the 0.85. Your X. Hey, you know what? Hold on. We didn't write this stuff down. Let's go back. I didn't write anything down. I wrote P naught down, that's all. Okay, sorry, let's find X. Okay, let's start with n. I like to do n first. Okay, so n is equal to our total number. Conducts a random survey of 200. Okay, so n equals 200. And then remember, x is the people that have a certain characteristic. So x is going to be all those people that, you know, eat salad at least once per week. That's going to be 171. Okay. And then our alpha here, 0.01. Okay. Sorry. Now we can do the test statistic because now we know all that stuff. So x is 171. N is 200. And we were testing to see if it was greater. Calculate. Okay. So here's our test statistic. Z naught is going to be 0.198 or 0.20. So let's see here. Oh. Okay. 0.20. And then our p-value, which was right below, was 0.4215. Yes, 0.4215. There we go. Okay, so now, again, you can use either approach if you want to do the classical approach or you want to do the p-value approach. If you're wanting to do the classical approach here, then I'll point out that actually your critical values will be on your formula sheet for this. It's on the third page. So if I wanted to do the critical value here, Z critical. Oh, just to be clear, this is your test statistic, okay? What you pull off the calculator. And then this is your p-value here. Okay, but if you want the critical value, for this one, all you have to do is look for your confidence level. So we're doing, whoops. Here it is right here at the top. Critical values for the standard normal Z distribution, right? So we are doing a right-tailed test because it's greater than 0.85. And our alpha is 0.1, right? Or is it 0.1? Or what was it? Alpha, oh my goodness, I'm sorry. Oh my gosh, I'll get there. Alpha's 0.01. Okay, so 0.01. Okay, so here it is. 0.01, right-tailed test, it's 2.33. Okay, 2.33. So, all right, so if you wanted to draw your graph, 2.33 is over here. That's, of course, 0. Your critical region, this is the critical region here. Okay, and then you want to know where does your test statistic fall. And your test statistic is going to be about there. So it looks like this is a do not reject also when you're looking at your picture here. See, this one's a lot easier to do than the T stuff. So do not reject. Again, this is just one way to do your final conclusion. Now, if you do the p-value approach, right? So for p-value, you're going to compare 0.4215 to 0.01, which is your alpha. And so it looks like this is greater. So again, if p is greater than alpha, we do not reject the null. Okay. So final conclusion, there is not sufficient evidence at the alpha equals 0.01 level of significance to conclude that the percentage of Americans who eat salad at least once per week is higher than 85%. Okay, there we go. So there's not enough evidence to support her claim. Okay, which is kind of not surprising at all. For me, it didn't seem surprising that there was not enough evidence to support the claim that more people than 85%, or sorry, more Americans eat salad at least once per week. Yeah, I thought that was, yeah. I'd want to know about a study about pizza or something, like how many people eat pizza at least once per week, you know? Okay, let's see where we're at on time here. Okay. A professor wants to know if online homework improves his student grades on the final exam. He randomly selects one class that uses online homework and one class that does not use online homework, both in the same subject. At the end of the semester, he summarizes his findings, test at the alpha equals 0.1 level of significance. Okay, so we've got a class here. We've got 27 students in a class that use online homework, 25 that do not use online homework. We've got their mean final exam score and then their standard deviation. So let's see here. Are we looking at means or proportions? Probably going, well, you said mean final exam score. Yeah, you're right. It's two means, right? Two different means. One's online, one's without online. So we have two means. And these are independent. Okay, they're independent of each other. Because you've got one of them that's doing online homework, one of them is not doing online homework. So they're separate from each other. So our hypothesis, let's start with our hypothesis. So how do we do two means hypothesis testing? Well, let's just call this one to be mu1. mu2. Well, actually, I don't want to call it mu1 and mu2. I'm just going to call this sample 1 and sample 2. How about that? Okay, so our hypothesis test. How are we going to do our hypothesis test? So let's see here. We're going to do H0, H1, and H0 for two means that are independent samples. It says we set mu1 equal to mu2. Okay, to see if they're the same, right? That's what we're testing. Are they different or are they the same? Well, actually, let me see. What did he say? Let's read it again to see what we do for our second one, because we are going to do mu1 and mu2 here. The question is, what do we put in between? So we're looking for some keyword. Professor wants to know if online homework improves his student grades on the final exam. At the end of the semester, yeah. So it looks like he wants to know if it improves, right? So he wants to know if online, so that's the first one, if that's more than the second one, right? That's what we want to know. Okay. Now, of course, that might be different if we labeled these differently, right? If I said that sample 1 was without instead, right? Maybe I said that without online homework was sample 1, then these would actually be, I would have a different inequality here, okay? So just know that when I say it improves, we're saying online homework improves grades. So that means online is better than not online, is what the hypothesis is. Okay, so if we want to find a test statistic here, then we're looking at doing, let's see, let's find some other information. What all do we need to pull out of here? Well, I've got sample 1. I've got sample 2. So sample 1, let's do this in order. N1 is 27. Mu1 is 73.6. And, oh wait, is it mu1? No, it's not mu1. I'm sorry, hold on. It's a sample, right? X bar 1. And then S1, 10.3. Then for sample 2, we've got N2, 25. X bar 2 or X2 bar, I don't know how you want to say that, 67.9. And then S2 is 12.4. And then the last little piece that we need here alpha equals 0.1. Okay. So let's go to our calculator. What do we, well, actually, hold on. Before we do that, let's see. 2 means independent. If you look on your formula sheet, it says we want to use a 2-sample t-test. So I'm going to put that up here. 2-samp t-test. Okay. So let's go to our calculator. That's not my calculator. Okay, stat, tests, 2-sample t-test. Make sure you choose the t-test, not the z-test, the t-test. Okay, that's number 4. Okay, and we have the stats. Okay, so X bar 1. Oh man, I should have put those in a slightly different order. Sad. Okay, X bar 1, 73.6. S1, 10.3. N1, 27. X bar 2, 67.9. S2, 12.4. N2 is 25. And we are testing whether mu1 is greater than mu2. Sorry, I got that one. Oh, yes, and always leave pooled on no. It should always default to no anyway, so just make sure you leave it there. And then hit calculate. Let's see what we get here. Our test statistic is going to be 1.795 or 1.80. And our p-value is 0.039 or 0.040. Oh, wait, hold on. Let's do 4 values. 0.0395. Yep. Okay, so let's write those down. You'll notice it also gives you degrees of freedom and stuff, but we're not going to do all that. Yeah, don't worry about all that. So, we're just going to write down the test statistic because we didn't really even cover that in our notes. But we can find the test statistic. That's not hard to do. And then on the next page here, at the top, I've got my p-value, 0. Sorry, I had to go onto 2 pages. I didn't want to waste all that space, though, to try and put it all on one page. Oh, p-value. Okay, and because we're not even going to test it using the critical values and all that kind of stuff, I'm just going to go ahead and write the alpha over here. Alpha was equal to 0.1, right? So let's compare 0.0395, 0.1. Okay, so right after the decimal, right? This one's 0, this one's a 1. So p is less than alpha. Oh, finally. So if p is less than alpha, that means that we reject the null hypothesis, right? Okay, so if we reject the null hypothesis, then what does that mean? We say that there is sufficient evidence at the alpha equals 0.1, a level of significance to conclude that what was it? That online homework improves student grades on the final. Okay, there is sufficient evidence that the alpha equals 0.1 level of significance to conclude that online homework improves final exam grades. Okay. Okay. Letter F says, use a 90% confidence interval to determine on average how large of an increase in final exam grade do we expect to see from using online homework. Does this look like adequate justification for using online homework? What are the problems with this study? Okay, so this is like, I'm going to tell you a super long explanation in my key. And I'm not going to ask you something like this on the final. So I wouldn't really honestly worry so much about this one. We will find the confidence interval. And I'll discuss it, but I'm not going to write it all down. It's just too much writing. Okay, so 90% confidence interval. All right, so my C level is 0.90. Okay, and so let's go to, let's see. We're going to do the 2 sample T interval, right? So 2 samp T int. Okay, so stat test 2 samp T interval. Yes, make sure you get the right one. Okay, and we have, oops, stats. Okay, so let's see. Did it carry all of our stuff in here, right? 73.6. Oh, good. Okay, I don't have to retype any of that stuff. Okay, but my confidence level is 0.9, right? So I think we're golden. Okay, 0.9. No. Calculate. Cool, we don't have to retype anything. Okay, here it is. 0.37, 11.03. Okay, so here's our confidence interval. The question is 0 in the interval or not? Remember, because that'll tell us if there's a significant difference or not. Now, I would say, if you look in this interval, this is positive, right? And so that means 0 is not in this interval, okay? If 0 is not in the interval, then there is a significant difference, right? Significant difference. Okay, and vice versa. If 0 is in the interval, then there's not a significant difference. And remember, the reason is because if you subtract the two things and they're the same, right? If you take them and you subtract them and then they're the same, you get 0, which means that if 0 is in there, that means that they're the same. So there's not a difference, right? But if you're looking at this, you're saying, okay, 0 is not in there, right? So that means, yeah, there's a significant difference. Okay, so here's the thing. Does this look like adequate justification for using online homework? Okay, well, here's the problem with this, right? There is evidence that the online homework improves this final exam, right? However, they're saying that the improvement is anywhere between 0.37 points and 11.03 points. So depending on whether or not you're increasing by, if you're increasing final grade by 11 points, that's an adequate justification. You're like, wow, look, this is like a whole letter grade, right? That's a huge leap. But if you're only increasing by 0.37 points, that's nothing, right? That does not prove anything about the online homework, right? So I would say that this is a problem because of really the small sample size. It says, and so here's what my answer says. We do not have enough data values to determine if online homework is justified or not. A major problem in the study is the small sample size. If the distribution of final exam grades is not normally distributed in both samples, then the results of the study are invalid, right? Another problem would be that the professor randomly selected entire classes instead of using a simple random sample of students. Thus, there may be dependence in the selection process, and we cannot determine if n is less than 5% of the whole population. So, several issues with this one. Okay. So I think I might go ahead and end the video there. No, I should probably do D in this video, but I have to pause for it. Okay. In the excuse me. In the General Social Survey, random adult Americans were asked if they were healthy and if they are happy. Of 2,569 people who claimed to be healthy, 2,499 also claimed to be happy. Of 162 people who claimed to be not healthy, 123 also claimed to be happy. Test at a 5% significance level if the proportion of healthy adults who claim to be happy is higher than the proportion of unhealthy adults who claim to be happy. Okay, so let's see here. First of all, let's look at, are we dealing with, first, yeah, it says what type of test is being run here, right? Well, it looks like, first of all, I see the word proportion. So I know I'm going to deal with proportions here. And the other thing is I see that there's like two different types of proportions, right? They're talking about people who are healthy and happy, and then people who are not healthy and happy. So it looks like we're going to be comparing two different proportions, right? So to test at a 5% level of significance, if the proportion of healthy adults of healthy claim to be happy is higher than proportion unhealthy claim to be happy. Okay, so yes, we are doing a two proportions that are independent. Two proportions, they are independent. That's where I wanted that actually. Okay, so let's figure out first, I guess, what do we want to call like healthy and unhealthy, right? So let's see here. We've got let's make our first sample sample 1. We'll say these are the healthy people. And sample 2, these are our unhealthy people. Okay, so let's see. That means that this will be like our P1. Sorry, that's like a lowercase p. I should redo that. It should be P1 and P2, like that. There we go. Okay, so P1, P2. Okay, so our null hypothesis, and then we have our alternative hypothesis. So for the null hypothesis, since we're comparing two proportions, we should have the first one, and on your formula sheet, it'll say P1 equals P2 as the way that you're going to set up your null hypothesis. So that shouldn't be a surprise, right? That's going to be the first one. And so we want to know, okay, for our alternative, it says the proportion of healthy adults, so this is P1, is higher than unhealthy adults, so P2, right? So we want to know is P1 greater than P2, right? Higher than, right? That's our keyword. Okay, so let's go ahead and list out everything that they gave us in the problem. I'm just going to put like a little healthy. This is our first sample. And then I'll put unhealthy here. That's number 2. Okay, so let's see. Let's go back. Random adult Americans were asked if they were healthy and if they are happy. Okay, of the 2,569 people who claim to be healthy, did you guys just see the little battery power thing pop up? I wonder. I would assume it popped up on my screen and you see my whole screen. Well, I guess my battery's getting low. Okay. All right. So the healthy people, so N1, that total is 2,569. And it says the people who claim to be happy. So remember, that's our certain characteristic, right? So this is our X. So X1 is a certain characteristic. And this characteristic is the people claiming to be happy. So there's 2,499 of them. And well, I guess that's all, right? For that, I guess I don't need such a long line. It's probably good. So then what's the size of our sample for the unhealthy people? It says of 162 people claim to not be healthy. Then out of those, 123 said that they were happy. All right, man, those are some very different sample sizes, huh? 2,500 versus about 150, 160, I guess. That's a fairly significant difference, but we're just comparing proportions, right? So let's go to our calculator because we are using, so two proportions, right? So again, if you look on your formula sheet, in order to find the test statistic and the p-value, we will use, I don't even have space for it, I'll write it here, 2 prop z-test. Remember, prop for proportions, 2 because how many proportions we have, and then the z is because we use proportions, right? And test, of course, means that we are doing hypothesis test. Okay, so we are looking at stat, tests, 2 prop z test. That would be number 6. Enter. Okay, so X1 was, of course I put them in the wrong order, 24.99, oopsie, 24.99, and then N1 was 25.69, X2 is 123, and N2 was 162, and we wanted to compare whether or not P1 was greater than P2. Oh, good, I already have there. And we will calculate. Okay, so our test statistic here is 13.4, wow, 13.46, and our P is 1.33, and you're going, wait a minute, I thought P was a probability, right? Shouldn't that be between 0 and 1? And I would say to you, you're absolutely right. It should be between 0 and 1. So look at the very end here where you see it says E negative 41. E negative 41. Okay, just let that sink in for just a minute. That's scientific notation. That's a negative 41 on the 10. Okay, so let's go back, shall we? Let's write this stuff down. Let's see. Okay, so our test statistic was z equals 13, which, by the way, generally, if you remember, our z-scores are generally between -3 and 3, unless they're somewhat extreme, and then sometimes they're, a little bit farther away, maybe 4 or 5. I've even seen 7. 13, I mean, that's crazy. I mean, it's just crazy. So really far away. And then our p-value, we said, is 1.34 times 10 to the negative 41. Okay, so honestly, we can't even write that as in standard form. I mean, what, you want me to take up the whole page, right? If I did that. So I'm just going to put over here, this means P is essentially 0. Okay. Negative 41. That means you're moving the decimal 41 places to the left. So that's a decimal with 40 zeros and then the 1. I mean, if you're talking about impossible, I'd say that's pretty much it, right? So let's compare. So we could do the test statistic and, do the critical value thing and classical method, all that, but I'm not going to. I'm just going to do the p-value because we've done classical method and you know how to do it at this point. So if you really like that, which most people don't, go for it. So the test statistic's definitely going to be in that critical region. It doesn't even matter what the critical number is. I mean, that's in the critical region. I'm just saying. But okay. So let's compare our alpha. So let's see. Alpha was, I didn't even write that down, huh? Alpha, it said 5% significance level. So alpha is 0.05. And actually, you know what? Hold on. I feel like I'm needing a little bit of color here because this has just been kind of not colorful. So here we go. There we go. That's much better. Okay, so let's compare P to alpha. Is 0 less than or greater than 0.05? Obviously. Okay, so P is less than alpha. Doesn't really matter what your alpha is, right? So when P is less than alpha, then we, of course, reject the null hypothesis. So when we reject, what we would say for our final conclusion is there is more than sufficient evidence. Sufficient evidence to conclude that. I'm not even going to put it the alpha equals 0.05 level of significance because it doesn't even matter, right? I mean, at any level of significance, this is true. Doesn't matter. So I'm not even going to state that. There is sufficient evidence to conclude that the proportion of healthy adults who claim to be happy is higher than the proportion of unhealthy adults who claim to be happy. I did it. I made it fit. All right. I think there's one more part to this question on the next page. So let's see here. Yeah, it says use a 90% confidence interval to determine how much higher is the percentage of healthy people who are happy. How does the confidence interval support your decision about the null hypothesis, right? Okay, so let's make a confidence interval. Okay, so when we're doing a confidence interval for two proportions, we're going to use the 2 prop z int. Okay, and so some of the stuff that I think we're going to need is the stuff that I had written down on the previous page, which was that I'm going to actually switch the order, that x1 was 24.99, n1 was 25.69, and I think it'll actually have this in the calculator already for us, but just in case. 123, 162, and then what is our confidence level? So our confidence level here, so C level 0.90. Okay, so let's go on our calculator. 2 prop z int, clear, stat, tests, 2 prop z int. See, I don't see it here. I hit the up arrow. Oh, here it is. 2 prop z int. It's letter B. Okay, so good. It did put it in there for us. X1, N1, X2, N2, confidence level 0.9. All right, good deal. Let's hit calculate. Okay, now I say it put it in there for us. I will just say if it's not in there for you, it could be that this was the last question I did on here like this, and maybe that's why it's in here. I don't know. I think it's going to be in there for you, though. Okay. All right, so here's our interval. 0.158 up to 0.269. So let's go back. And we'll say, all right, it's 0.158 to 0.269. It's our interval. And then the question says, how much higher? So use this to determine how much higher. Okay, so it's going to be 0.1, or sorry, I guess if we did this as percentages, we could say 15.8 to 26.9% higher. And then it says, how does this confidence interval support your decision about the null hypothesis? Well, remember that if we were comparing, we want to know, is 0 in this interval? And if it is, that means that there's no difference, right? And if it's not in the interval, then that means there is a difference. So I guess I'll start with the first thing, which is use the interval to determine how much higher the percent. Oh, it does say percentage. Oh, highlight percentage of healthy people. Okay. So let me say the percentage of, I just don't know if I'm going to have enough space here. Well, I should have definitely left some more room here. I will say we are, oh, I know. I'll just erase this stuff. Okay. We are 90% confident that the proportion, no, I'm sorry, percentage of healthy adults who claim to be happy is 15.8% to 26.9% higher than the percentage of unhealthy adults. Who claim to be happy. Okay, sorry, and then the other one says, how does the confidence interval support your decision about the null hypothesis? And that's where we would say, we would go ahead and look into whether or not 0 is in our interval. So I'm just going to maybe, over here on the side, I'm going to say, okay, so our interval is, so I'll try and go back and add some space here to this before I post it. That way you have a little more space to write this stuff down. This is a plus, and that means that 0, so since 0 is not in the interval, then it supports, or I guess we have confirmed that there is the null hypothesis of no difference. Since 0 is not in the interval, we have confirmed ugh, this looks so messy. That H naught should be rejected. Okay. Yeah, I'm definitely going to leave you some more space when I go online to do that. Okay, letter E says, circle the correct words. In a test hypothesis, we assume that the blank hypothesis is true. Okay, we assume that the null hypothesis is true. Actually, you know what? I'm going to highlight this because I think you can read that better. That the null hypothesis is true. Then we calculate the probability of witnessing our sample or a sample either farther away or closer to the null hypothesis. Let me see. We would say that it would be farther away from. Okay, we calculate the probability of witnessing our sample or a sample farther away from the null hypothesis. If this probability is unusually, so this is your P, right? So if we witness our sample or a sample farther away from ours, then from the null hypothesis, right? If this probability is unusually low, right, because we compare it to alpha to see how low it is, then we would reject the null hypothesis and right, if we find that the probability is very low, so if P is less than alpha, we reject the null hypothesis and then we support the claim of the alternative hypothesis. Okay, let's see here. I got number 20. I got only 2 more pages. This video is already at 1:25. I'm gonna probably go ahead and I'm gonna go ahead and stop this video. I'm gonna make one more video for the last 2 questions.